All right. So this idea of entropy and thermodynamics leads us to being able to predict the number of defects in a given material at a specific temperature. So that's what we're going to talk about in this module, the equilibrium number of defects. All right. So we didn't sort of go through the derivation of this because this isn't a thermodynamics course, but the result of that discussion of energy cost and entropy or disorder is that we're able to predict or expect a certain number of defects with temperature. So we're able to formalize that idea. And we do it with this equation here for vacancies in particular. So this is for vacancies. And if you see the equilibrium number, that's because we're talking about thermodynamics, and thermodynamics is all about the study of equilibrium. So that means when the system is at rest, it's not changing. So if the number of vacancies is still changing, that's not equilibrium. So we have to wait for some amount of time before we get the equilibrium. So again, this is a topic kind of beyond our discussion here, but this will be covered in other thermodynamics courses. But for now, if you see that, just know that it's kind of steady state. We've waited for the system to stabilize to a specific number of vacancies. And that's what this equation gives us. It gives us the equilibrium number of vacancies, N sub V, and that's a function of the total number of atomic sites that we have. And so this is typically reported as sites per volume, so 1 over meter cubed. And so that would mean that the equilibrium number would also be in those same units. And then here, this is the exponential. So if you see this terminology, this is the same as e to the power of. So some people just haven't seen that before. So the exponential exp just means exponential. So that's e to the power of some number. So that's what we have here. So in engineering, we just like to use this exp. So we have the total number of sites multiplied by the exponential of a term in here, which is negative, and then QV, which is the energy required to form a vacancy. And that's going to be in energy units, so joule or electron volts per mole. So we're normalizing this per mole. And then below that, in the denominator, we've got Boltzmann's constant, which is a thermodynamic constant, which is given here, and that is in joule atom K, so joules per atom degree K, and then temperature. And this is in K or Kelvin as well. And that's an important thing to keep in mind because this isn't a thermodynamics course, we don't have more time to discuss. But you remember we talked about the absolute zero, which is 0K. So that's an important thermodynamic concept. And so whenever you're dealing with thermodynamic equations like this, you always have to use temperature in K, not Celsius or Fahrenheit, because we're always referencing to that 0 point. And so if you're ever in doubt in thermodynamic equation like this, where you're talking about equilibrium and you see temperature, just always use K and you'll never go wrong. If you try to use Celsius in some equations, it will not work. It's not the same as being able to convert because we're talking about a reference point to 0. All right, so this allows us to calculate the equilibrium number of vacancies, and we see it's a function of temperature, and so we expect more as the temperature increases, and it's also related to this energy required, right? And that's what we saw. It's the energy to pull an atom out of a lattice site. So this is about the energy required to break those bonds in that specific structure. So this is going to be tied to the material and the structure that it's in. All right. So we can also we see that we, in this case, we talked about the number of vacancies per volume. Sometimes you want the absolute number of vacancies, not the volume weighted version. And so we can actually solve for that in terms of this equation here. So essentially this would give us the absolute value. So the total number of sites, again in units of sites per volume, and we can calculate what that is for a particular material if we know its density and atomic weight. So that sometimes has to be calculated. However, we can also solve instead of trying to solve for the absolute number of vacancies per volume, we can also solve for the fraction. So if we basically move that in here to the left side of the equation, we see that we have number of vacancies per volume over number of total sites per volume. And so we have a fraction. And so oftentimes this is all we need is what fraction of the sites are vacancies. And so in this case, we could just use this expression and we don't have to calculate for the absolute value, etc. This is just going to be a unitless fraction. And so it doesn't require us to solve for the total number. All right, so in the next module, we'll go over a specific example with this calculation and see what the implications are for temperature and the number of vacancies.